Going to work a case study here of a vehicle suspension model. Now, a suspension model by itself is pretty much a vibration model, and if you were just studying vibrations, you might take different approaches using a bond graph. But what we're going to try to do is show how you can integrate an actuator model and try to integrate some of the concepts that we've talked about in building bond graphs. And what we'd like to do is show you how to put together smaller models that you might build with a bond graph and show how then you can interconnect them to create the full model of a system. This will be a good lead-in before we begin talking about causality and how we could use a model such as that to derive equations. But even better than that, we can use causality to check our model, and that's something that we'll be talking about shortly. So let's start off and have a front view here of a typical Humvee. And what we're going to do is build, if you're familiar with any vehicle dynamics modeling, a quarter car model, typically what you might start off doing in studying the suspension is really just looking at essentially a fourth of the vehicle and just studying the response dynamics of that. And as you can see in the front of this Humvee, this actually has an independent suspension. And what's often done with modeling suspensions of this type, you can assume that that you've got the tire, and in this case, obviously you've got this suspension here, and there's a strut inside. It's like a damper, and then you've got the spring. So and then that's hinged up here, if you like, to the main body of the vehicle. So you've got some mass down here of the vehicle, and then you've got more mass up here, right? And between, if we take the mass of the vehicle at the center, we're going to have, of course, the contact with the ground, and so there's going to be some stiffness and some damping, here as well, right? So let me clear that up a little bit. So that is at least the conceptualization of what a quarter car suspension model looks like. Let me show you on the next slide. Here I've collected sort of three forms of that quarter car suspension schematic form. You can see the fourth of the mass of the vehicle that you might take of the body of the is usually called the sprung mass. Any mass associated with the wheel and the tire usually refer to that as the unsprung mass. So you can see you have two masses here, and we assume we have vertical vibration in this simple case. And you can see the spring damping of the tire connecting to the ground. And then, of course, between the sprung mass and the unsprung mass, you have whatever kind of suspension characteristics you might have. Here's your typical passive suspension, to spring damper in parallel. And then here, this shows an actuator that might be used for load leveling, right? So you could raise or lower the sprung mass, but you still have passive elements here. And then here you have what you call like a fully active suspension, where in parallel with a passive spring, you might have an actuator of some type. This shows both of these actuators look like hydraulic piston type actuators, right? But this could be any kind of actuator. You can see it's between the sprung mass and the mass. And we're going to build some models here. And again, these are just for practice in building a bond graph for these systems. Now, before we tackle this full system model, let me just show you in the next slide what the next step might be. played around with this model before, right? It's a simple mass spring damper system, but remember this is the ground excited or base excited mass spring damper system. And the reason I want to throw this one in here is if you understand how to model this one, the step up is that much simpler to do the full quarter car vehicle model. Also, we want to talk a little bit about how we might model the ground and what the input might be. And we talked a little bit about this in previous videos and lessons. Okay, so how would we go about modeling this system with a bond graph? Okay, now I'll assume that you could build a free body diagram and take a straight vibration model approach, but again, we're trying to practice bond graph modeling. One thing that you can do is start off with the mass and put a 1 there because we know we have a velocity associated with that sprung mass. So I'm going to put a mass here. Okay, and that mass also has, if we want to include the mass times gravity as a force here, and because that's acting down, we're going to put power away, meaning this is a force that's going to work against the increased momentum of the sprung mass in the vertical direction, right? Because our sign convention is positive up this way. Now, how do we deal with the rest of this? How do we connect this suspension? How do we take into account forcing from the ground? Well, the forcing of the ground, and the Vx here shows the sort of the overland velocity, call that Vx. We're going to assume that this vehicle is moving over the ground at some velocity v sub x, but we're interested in modeling the vertical dynamics. So if we assume that, and this is really an idealization of the tire following the ground as it rolls, that this is going to follow the ground displacement that you will assume to know as a function of x, where x is the position along, right, the longitudinal direction, if you like. So if we know the ground displacement as a function of position, and we know the forward velocity, what we want to find is what is the velocity of this point in the vertical direction, because that's going to be our input here. So let's assume first that we have Vg, and then I'll show you how you can find Vg given that you know the ground displacement and also the overland velocity. So you have a velocity of the ground here, you have a velocity of v sub s, so you have two velocities, and here's a little trick that we'll often use. We have one velocity there. Let's put another common flow velocity point down here. These are two distinct velocities, and what separates them, right, is these two elements that each have also the same velocity, but that velocity is different. That's the velocity that you're compressing that spring and damper at. So we need to create that difference. Here's one little trick that we'll use often is we can use a 0 to create that velocity. This velocity here is our v sub g, right? Here's our vs, and that difference here is, let's call that delta v. That's that difference velocity between these 2 points. And I need to have a 1 there because I want to attach on that common flow 2 components, my spring and my damper. And these are linear elements as shown, so I'm going to put those parameters here the way I would do. So I've got this 1 here, and I'm going to assume that I know that as a flow source. So I'm actually going to put a flow source in here because I'm going to assume that I know v sub g. I can eliminate this 1 later, and I'll show you tricks for doing that. Okay, so I've now completed that model. I have a 0 here, 1 here, and another 1 here because I want to make sure that I constrain those 2 components to have the same velocity. Now, how do I find Vg? Well, what is Vg? Vg is the derivative of Zg with respect to time. And since I know zg with respect to x, right? That simple chain rule. Right? And this value here is what? It's that forward velocity. This is simply the derivative of the known function zg with respect to x. So this allows you to compute vg as a function of time, given that you know the position, rather the elevation as a function of position, and of course your forward velocity. Now, as you can see here, the reason why it's worth working that simple mass spring damper ground excited problem is because then understanding how to handle the full quarter car model, where you have tire stiffness damping, ground excitation, unsprung mass, right? Sprung mass, suspension characteristics, now is really just a simple extension. I'm not going to work the full model. The only thing that you have to realize here, the key thing, and the reason I like to introduce this problem is because this working vibration problems then becomes pretty easy, because you see this a lot where you have masses, velocity, with known, there's a distinct velocity here, distinct velocity here, and a distinct velocity here. And on all of these problems, it becomes simply a matter of throwing down ones, creating velocity differences, and then attaching spring damper. Power always into passive elements. And that's all I'm going to work on this slide, because the rest is the same. You now just have two stages of this problem. This is the input here, and so on. Okay. You can imagine now working more complex vibrational problems, whether they're translational dynamics or rotational dynamics, with combinations of masses and springs, becomes then often a combination of using and recognizing the use of this very useful construction of finding that you've got stiffness dampers in parallel, common velocity, and so on. Now, moving on to understanding how to put a suspension in here becomes that much easier. Where do we put, an active suspension? Where does an active suspension go? Well, this is the tire. We need to introduce possible active suspension elements between the mass, the sprung mass, and unsprung mass. So let's look at how we would go about doing that. So I've pulled in a couple of different pictures here. Some of you may be familiar with suspension placements and actuators, and where you might put actuators, given some understanding of suspension geometries. And I'm just showing here as an independent suspension, typical independent suspension. Here, that this shows solid axle suspension, but the idea again is you want to put your actuator, in place of these elements here and here, as we've already discussed. I inserted here, here at the University of Texas at the Center for Electromechanics, they have a long history in a research program of working on an active suspension initially for M1 tank, eventually evolved an application to actually the Humvee, and later into trucks. And this shows some of the different actuators that they've worked with. And basically what these are motor kind of rack and pinion type actuators. And we've looked at rack and pinion examples, but this is a linear actuator that can be inserted in this location here. And actually this shows sort of a detail of how that is placed between, again, the vehicle body and the axle of the wheel axle. So you can see that actuator is inserted right in there. I'm just showing this here to illustrate how you might put that into a solid axle as well. So now in schematic form, you can see your actuator, and I'm showing the actuator as a blue element here, is creating a actuation force. If we do a little free body diagram, you can see that the actuator force is going to have the same velocity as your spring and damper if you want it. Typically, and oftentimes in an active suspension, you'll eliminate the damping element and incorporate any kind of passive damping into the control of your actuator. So you can see then, remember when we talked about creating that velocity difference between unsprung mass and sprung mass in a suspension, because you wanted this difference velocity, and that's the difference velocity that's being created here, and this is that velocity here. So your spring, which helps you support you statically, is always here, but now remember we used to have a damper here as well. Well, now we're going to actually, and power would flow into these passive elements. Now we're going to put an actuator here, and I'm going to change the direction of the power. Now I'm putting power in. So this is how you would put in your active suspension into your overall model. Now let's see if we can create here our overall suspension model, full quarter car model with a model of the actuator integrated. I'm going to begin where? Well, I'm going to begin with the input ground velocity. Remember that goes and that gets split off, and you've got your tire stiffness and your tire damping. Then you have to go into your tire mass. Of course, this is tire and wheel mass, and also, you might put in your gravitational force there. And now you've got to create another difference here, and here's where your suspension goes. Okay, and I'm going to stop there because I want to build the rest of this first. And here is sorry, let's use common notation. This is the unsprung mass and the sprung mass, and then here's your gravitational force there. Okay, so you've got your vehicle model. Now I want to include here the suspension stiffness. But then what I'd like to do here is say I'm going to create this actuator force. Now where am I going to get that from? I need to now build the rest of my model over here for my actuator. And let's say that I have a rack and pinion type system. So what might that look like? Well, you might have we may not end up building the whole thing, but let's say I've got real simple permanent magnet DC motor. Let's go ahead and put a simple rack and pinion element, right? And so here you can have sort of a gear connection, and you have a rack and pinion combination, so that you have rotation, translation, conversion here, right? And that's the actuator that you would have here. And the actual devices that were built at the Center for Electromechanics used different kind of motor, not a permanent magnet DC motor. They use brushless DC motors. There's also some damping in here. I'm trying to keep it simple, but so I'm going to back up here, and you can see the element here that I need is a coupler. I need a transformer that's going to have my and remember, this motor body is mounted on the vehicle body, and it moves relative to the unsprung mass. So that's that velocity here, and that's captured here, okay, through this difference. That's why we can mount it here. It might take a bit here to catch that. This is going to be the transformer modulus for your rack and pinion. This you might have, actually I'm going to put another T here because you might have a gear ratio, another gear, and then I'm going to keep going back and creating then the conversion, the electromechanical conversion here. I'm actually going to put, you might have some rotational damping, you might have some rotational inertia, and then you have the gyrator, right? That'd be a little tricky for you to build these backwards, but now this is we've built a permanent magnet DC motor model before, but you know that you need to convert to the electrical side, and here I'm going to go ahead and put the inductance, the armature, resistance of the armature, and finally over here we might have some voltage input to drive this here. And this, I'm going to show this as an effort source, but this would come from some control system. So look at what we've done. We've built a complete suspension model. It's ready for us to do analysis on it and to derive equations, and that's what we'll be doing in subsequent videos, is learning how to apply causality and how to derive equations directly from a model that we've constructed in a bond graph form.